you all know that nuclear reactors are powerful sources of electron antineutrinos. They come from beta decay of fission fragments and have energies typical for beta decay, few MeV. And reactors are there, they exist, they were built not for study of neutrinos. So in that sense, this is similar to atmospheric or solar neutrinos. The source is there to be used. So I was asked to review for you some of the history of using reactor neutrinos to study neutrino properties, and starting right after the Reines-Cohen experiment in the late 50s up to the current experiments, so I will stop somewhere in early 2000. So this is a story which is not like some of them stories which were told today, ready for Hollywood's thriller. It's steady progress to find things which we are interested in. So I divided this whole period into roughly 3 parts. In 60s and 70s, somehow neutrinos were not the hot subjects they became later. So Fred Reines and his collaborators were really the only people working with reactors, and they explored what one can do. They were real pioneers in that field, and they were able to study neutrino interaction with protons, the standard reaction, but also with deuterons and electron scattering. And then came 80s and 90s, where now the neutrinos and oscillation became the hot subject, but it wasn't clear where to look with reactors. So people looked where it was easiest to look, namely close to the reactor. So large number of experiments were performed, and I will mention some of them. And then later on, oscillations were discovered with solar neutrinos and atmospherics. So it was more or less clear what the delta M squares are, and therefore what the oscillation length is. And then it was clear that one has to look at 1 or 2 kilometers if you want to explore the oscillation related to the atmospheric delta M square, and that you have to look much farther, say tens of kilometers away from the reactor to look for the delta M square solar. And that was really done. So let me move on. Yeah, whoa, I think I skipped one. Here. So here are the list of the 4 reactions which were explored originally. Neutrino capture on protons, so-called inverse neutron beta decay, and the 2 reactions on deuterons, charge and neutral current, and neutrino electron scattering. Notice that the cross-sections are much smaller for these 3 than for the first one. Also, the threshold is somewhat lower. But nevertheless, all 4 were explored in this first period, and I will return to it a little later. So this inverse beta decay is the one which everybody uses, and that's because you produce a positron and neutron, you can detect both of them, and the correlation in space and time between the two is incredible results in incredible reduction of background. So that makes this sort of a little easier than anything else. So in the late 70s, the idea of oscillations became really hot subject. I remind you that the famous physics report by Bilenki and Pontecorvo was published 78. With MEV neutrinos from the reactor, the only thing you could do is to look for disappearance. And if you go away from the core up to, say, 100 meters, which was technically what was possible at that time, you explore delta m square around 1 eVolt square. And at that time, large number of such experiments were performed, more than 20, I believe 28 actually. Different people, different detectors, different reactors. They were all one detector experiment. So you place a detector at a certain distance and compare the signal with expectation, which has to be based on knowing what the reactor, what kind of spectrum the reactor is producing. All right, so the first experiment I want to mention is actually one which found hints for oscillations. That was, I believe, the first published oscillation paper. It was incorrect, it turned out. It was based on the beautiful idea of comparing the charged and neutral reactions on deuteron, which later led to Nobel Prize, but with neutrinos instead of antineutrinos. And the measurement suggested that the charge currents are suppressed compared to the neutral currents. So it turned out that this was, and here was inclusion plot, not exclusion plot, but inclusion plot with delta m square around 1 and large mixing angle. So the problem was that only neutrons were detected. So 2 neutrons were charge current, 1 neutron was neutral current. So you really had to know the efficiencies of your detector. The other problem is that the thresholds are sort of different. So you have to understand the neutrino, the reactor spectrum in some detail, which wasn't possible at that time. So this was withdrawn actually a few years later. So another experiment I want to mention is the first one where really the protons were used and where the oscillation was the main motivation. And that was done in Grenoble at the research reactor there, which was pure uranium-235. And the result is, here is a spectrum measurement compared to expectation, so no oscillation signal, and the ratio of the rates to expectation was compatible with unity. So in this context, since this is about history, I want to mention the importance of personal relations in this context. So the idea of oscillations was mostly discussed by theorists. And among them, back in Pasadena, Harald Fritsch and Peter Minkowski, who were there, and Pierre, discussed these things with everybody who wanted to listen, lunchtime and so on. So the idea of performing the reactor experiment was born out of these discussions. And then the question was, where would you put such an experiment? You will need friendly relation with the management of the reactor. They have to allow you to be on site and so on. So it turns out that at that time, Rudolf Messbauer was the director of ILL, and he was a former colleague from Caltech. So collaboration was formed, Caltech, Munich, and people from Grenoble, and this experiment was performed. Without these personal contacts, this couldn't be done. But there is a mystery about this first experiment, because 15 years later, it was realized, and that had nothing to do with neutrino physicists, that the power of that reactor was incorrectly determined by some mysterious error. So that in fact, that reactor didn't have 57 megawatts. It has 10% more. So 10% was missing. And this is unexplained to these days, why this experiment was missing about 15% of the neutrinos. And it cannot be anything fundamental, because later Osiris experiment, which was again pure uranium-235, similar distance, measured just one. So there is something funny about this. Anyway, all these one detector experiments requires that we know the reactor spectrum, what the fission does. And so this is a crucial part of all this, and I talk about it because I was involved. So you can determine that two ways. Either you say, this is from beta decay of these fission fragments, so I look at some data library and add the spectra of each individual beta decay together. There are about 6,000 beta decays. And the problem of that is that some of them were never measured, some of them were measured with large errors. So this is sort of difficult. You know, this is how it looks like. This is 6,000 beta decays. You add them up and you get the spectrum. So much more straightforward way is to use the fact that in every beta decay, you get electron and neutrino. And if you measure the electron spectrum associated with fission, that automatically adds all these 6,000 beta decays together. And then you have to convert the electron spectrum to the neutrinos using energy conservation. And that is a little tricky because you have all these different decays, different nuclear charges, but it can be done and tested without introducing more error. So these measurements of the electron spectrum was in fact done again in Grenoble by Klaus Schreckenbach and collaborators in 80s and 90s. And remarkably, all what we know about the reactor neutrino spectrum is actually based on these measurements. And this is one of the few examples that such a fundamental measurement is based only on one experiment, never repeated, never really tested. There is maybe there is no problem with that, but it's worth mentioning because the current experiment, some of you know, actually see features in the spectrum. So here is an example of the measurement of Schreckenbach of the spectrum. This is fast falling function. And it seems that today the current experiment predict that somewhere here there is a shoulder on that spectrum. And if you plot it as a ratio of measured to expected, you see a bump, a peak at around 5 MeV. And that has been now seen in 4 current experiments. So that casts some doubt on these electron measurements. And the other possibility is that there is something wrong with these 4 current experiments, which all are in some sense similar because these are large homogeneous detectors. All 4 of them use gadolinium to capture neutrons, and maybe there is something fishy about it. So you can look back in history. There were tests of the spectrum, and here is an example. That was an experiment performed in France, in Bouget, and what is plotted is the ratio as a function of positron energy of the measured to expected. This is kinetic energy of the positron, doesn't have the annihilation. So the bump should be here, and measured in Reno and Diabay and Double Show, it's about 10%. So it's not here. Clearly it's not here. So, and this was a different detector. This was segmented detector, small cells, measured only kinetic energy, the annihilation radiation escapes. So the question is, maybe it has something to do with that bump. Why isn't here and is in this modern experiment? So we decided to look at one of the old experiments that was done in Gascon in Switzerland, and the measurement was done at 3 distances. Here are the spectra, no oscillation, no change with distance. If you look with magnifying glass, you can see that always at around 4 MeV there are high pins. So Victor and Gabriel Žáček, who are sitting here, and they have access to these data. Actually, this was her PhD thesis, looked at it now, months ago. If you combine the 3 spectra together, because there is no oscillation signal, you can do that, you find you get a little improvement in statistics. You find indeed there is a thing here, and you plot it as this ratio. The red points are then Gascon points from the 80s. The blue are Reno experiment done now, and you see the bump is there. So clearly that bump existed already in the 80s. Unfortunately, nobody noticed that, or noticed that but didn't pay much attention, and that's a little bad because Schreckenbach was at that time in Grenoble measuring the electron spectra, so he could have solved this problem then, and not now 30 years later, where everybody is again looking at the reactor spectrum a few meters from the reactor core. All right, so now let me move on to the sort of the later state, around 1990s. As I said before, the oscillations were actually sort of observed, and one knew what the delta M squares R. So then you had to look at about a kilometer or two to explore the theta 1-3, to the oscillation between electron and muon neutrinos, which were not constrained by the atmospheric results. Because of the anomaly, we heard about it this morning, the fluxes of electron and muon neutrinos measured were roughly the same. And therefore, oscillations between muon and electrons will have no effect. So that led to, initially, to two experiments, Shaw and Palo Verde, at about 1 kilometer. And I will not talk about it more. You will hear more about it Friday morning. So I will concentrate on the experiment related to delta M square solar, where you have to go very far away, say 100 kilometers. The previous experiments were done up to 100 meters. So you go 1,000 times farther. So you lose factor 10 to the 6 million times in flux. That's a fantastic leap. So what you have to do, of course, you have to build a much, much larger detector. You have to suppress background many, many times compared to the other experiments. That means you have to go deep underground. The other experiments were typically on surface, because if you are 9 meters from the reactor, you cannot go deep underground. And you need to have more than one reactor. You want to have bigger flux. And so that sort of looks crazy. Besides, at that time, there existed two so-called solutions to the solar neutrino problem. There was a small angle solution and large angle solution. And people like Hans Bethe, who used to come to Caltech in winter, he said, oh, the small angle solution is so aesthetically pleasing, it has to be right. In that case, Kamland would be hopeless, I believe. John mentioned that. But nevertheless, this was possible to do because at that time, unlike today, in Japan there were 40 power reactors, and by some strange coincidence, many of them were built on a circle with radius around 180 kilometers, with center in Kamioka. Nobody knows why that happened, but that was the fact. So you had, instead of 1 or 2 reactors, you had power of many. Here is a plot. It's a flux as a function of distance. And in fact, out of these 40 reactors, 86% came from roughly 180 kilometers. That's that magic circle. So Kamland was not, strictly speaking, one distance experiment, but more or less it was. All right? Also, of course, the great thing was that in Kamioka, underground big cavern was available because this old Kamiokande experiment was dismantled and Super K was built nearby. So that place was available, again, without spending much money. Some money, of course, you had to do. The other problem was to suppress background. And you were deep underground, so the cosmic rays were not such a terrible thing, but the radio purity to get kiloton of liquid to be essentially without any uranium and thorium was a really major accomplishment. And you see 10 to the minus 18 grams per gram. That was never heard before about. But this worked. And even given that and given all these reactors working together, the rate was not so great. It was one event every few days. So the data came sort of slowly, but even the first result, published in 2003, showed that only about 60% of the expected flux was available, and that was in beautiful agreement with this large mixing angle solution of the solar problem. So this was already a great accomplishment. And then a few years later, you could see the details of the spectrum, which allowed you to get the delta M square pretty well. And finally, this is 2008. Here is the fit to delta M square and the mixing angle. And you see the delta M square published in PDG now is really sort of based on Kamland. The mixing angle is not determined very well. It is constrained much more by the solar. This is this potato, and this is from the Kamland. And if you are really purist, some people see some tension between these two, but I think this is second order effect. So I think I'm slowly coming to an end. So this is my last slide. Kamland was able, I think this was first time, to show not only that the flavor, neutrino flavor, changes, that neutrinos disappear with distance, but that it happens exactly the way quantum mechanics, simple oscillation theory tells you, namely that the flux goes up, the survival probability goes up and down and up and down. If you plot it as a function of L over E, there's again, for purists, there was not one L, there were many L's, and you had to subtract the geoneutrinos, but they were very small, as we heard just now, and in the background, and you have to divide by the reactor spectrum. But still, there is no cheating here. This is really the signature of oscillation, and we had big discussions in preparing this figure, and some of us said, oh, this we have to have, because this is what belongs to textbooks which talk about oscillation. So I will stop at this. Thank you.
Questions or comments? John?
So one little historical note of amusement. The circle of the reactors near Kamland was entirely fortuitous. The first plan of Atsudo Suzuki, as I think you may recall, was to put the detector in the mountains in Japan up nearer to Sendai.
Yes,
and in a deeper location and more convenient.
No, but I remember I visited Sendai and we looked at the map and there it was.
Right, but the real reason for going to Kamioka was political, not that. That was only, the nice circle was only noticed later.
Vigno, APC. You did not mention the Bugey result in '84, which showed also evidence for oscillation, and which was 3 years later. So the collaboration itself said that there was something wrong.
Yeah, well, I think that this graph which I showed shows that there are problems with that bump, and we do not have real explanation of it. And maybe it has nothing to, well, almost certainly it has nothing to do with oscillations, so you can say, forget it. But if it is there and it's not explained, it makes it a little troubling believing that we understand the spectrum well enough.
And why it's complicated to redo the Schreckenbach experiment?
Well, I think electron spectrometers are dying out. And you need a volunteer to do it. It's hard thing to do correctly, and so it doesn't bring you much glory.
I have a short comment and a question. A comment is that we should give more credit for Camland, also for excluding the magnetic moment solution for the solar neutrino problem. Because SNO is often said to confirm flavor conversion of solar neutrinos. In fact, it couldn't exclude spin flavor conversion. It would be the same neutral current signal if neutrinos are Majorana and there is Majorana magnetic moment. Yeah. And Camland definitely excluded this. So one more credit should be given to Camland for this, okay? Yes. That was common. And the question is, I heard from Schreckenbach, there was a funny heavy water, light water confusion in some reactor experiment. Can you comment on that?
Yeah, I thought that was behind this revision of the power of the Grenoble reactor. Mm-hmm. Somehow you measure the power by how much cooling you have to do, and then you have to plug in some constants, specific heats and whatever of the cooling liquid, and somebody simply entered wrong data. But I think because it's sort of embarrassing, there was never official explanation.
Are there any other questions or comments?
So Livia Rudova from Jülich. So I would have a question concerning the bump. You somehow undoubtedly attributed it to uranium-235.
No, I didn't.
That's what I understood. That's why I did not understand why.
No.
Okay.
The four experiments which see that are power reactors. So it's a combination of uranium and plutonium. And also the Gaskin and Boucher were power reactors. So no. But when I was talking about the first Grenoble experiment, it is pure uranium-235. Whether that's significant or not, I don't know. But there is a question whether the so-called reactor anomaly is related to all four of the fuels, or maybe U-235 is the only one. There is some indication now from Diabay that maybe plutonium is just as expected and that it all comes from U-235. There are other people who doubt it, and maybe we will hear more about it Monday. No, Friday. Monday we will be at home.
Marco Grassi, APC. I just wanted to ask if there was an experiment able to measure the antineutrino spectrum with very high energy resolution. Would this be valuable for the community? I mean, can we learn something more? Yeah,
but we have now say diabase has million events. So statistics is not a problem anymore.
I mean resolution with very
Yeah,
fine tuning.
so there is one thing is resolution. The other thing is energy response. Do you really understand what the energy of the neutrino is to give you what you measure is a positron response? So I do not see that if you measure with 10 kilovolt or something like that, that it will tell you much more than what we already know. The question which was asked is, you have these 4 elements which contribute, and in particular, uranium-235 and plutonium-239 gives the largest contribution, and if you can somehow separate that, that would be great. And research reactors are typically much more U-235, very little contribution from plutonium, so maybe that helps in separating the two.
There is no other question. Let's thank again Peter.